Hello. 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 Can you hear me?
We can hear you.
We start our lecture. Before starting the lecture, if you have any question, you can just ask, please. Hello.
Yes, hi.
Yeah, I'm saying that if you have any question, please just go ahead.
Okay. Regarding the lecture, or should we just wait for the others to?
No, we don't need to wait for the others. The time is already over, so we should start. They should be punctual.
Okay.
So how many people are in the room now?
4.
Yeah, it's okay.
4.
Hello, sir. Hello.
Yeah, hello.
And maybe Chandra's dog, I don't know.
Sorry?
And maybe Chandra's dog also. Bad joke. Joking.
I don't understand what you are saying.
No, I'm joking. I'm joking.
Okay. That is fine. Okay.
About writing in the lecture, it's
Mhm.
very difficult to understand because
What is difficult to understand? Can you please tell me? Can you see my screen?
yes, yes.
Yes, we
Okay.
can see it.
Because when you were writing,
Uh-huh.
sometimes it stopped showing.
Yeah, I checked it in even in my PPTs. When I was writing, everything was fine. But when I converted it into the videos, then this problem was occurring. Then I thought, okay, no problem. We can cover it in live tutorial right now. So if you would have the PPT, you can just at least you can listen my voice, so you can have an idea. So now rest of the things we will clear them now, right?
Yes, perfect.
Everybody can hear me clearly.
Yeah.
Yes.
Yes, sir.
Okay,
Perfect.
that's
And
good. Yeah. Hmm.
maybe if there's somebody in the waiting room,
I cannot
can you
see.
see?
Let me check. Yeah, please let me know if somebody else is also waiting, because when I will start my lecture, I will fully focus on my lecture. You can interrupt me anytime and just tell me that somebody is waiting in the waiting room. Okay.
Okay.
Okay. So we start our lecture. This is related to derivatives. Like, we used to take derivatives, and here again we will use simple derivatives, and we will study how we can use these derivatives in our real life. So to do so, first of all, we will have some basic definitions, and things are very simple, not complicated. So the section 1 will deal with the first derivative. I don't know how can maybe I can write on it, I think. Yeah. So we will deal with the first derivative and graphs. So the first derivative is associated with the slope of the graph of a function. Slope, like we have discussed the function of slope in fundamental mathematics, like it was uh, y2 minus y1 over x2 minus x1. We were denoting slope by m. Actually, slope is dy by dx. So the definition of derivative comes from the slope. Okay, that is something irrelevant. We will not waste our time on this. Next is increasing and decreasing function. And here you can see that we have written something. For example, in this increasing and decreasing function, we will use a definition which is called domain and range. Have you ever heard about domain and range?
Yep.
Okay. And do you know how to calculate it? Everybody knows?
Yes, I do know.
Huh?
I do know.
Okay. So for example, if you know, that is very good. Otherwise, I can just give you a slight overview about domain and range. Domain and range. uh, Domain is, I cannot write, you can just listen it. Domain is the set of all values for which we have solution, for which the function exists. For example, if I write y equals to x, can you give me any value for x for which y does not exist? You can substitute any value for x into this function and you can get the y. Is that clear?
Yes.
Right? So it means that the domain is the set of all possible values. So in that case, domain is x such that x belongs to set of all real numbers, or this is the mathematical way to write. You can write it even in words that the domain is set of all real numbers. Now I can give you a counter example. It would be more clear. For example, we write a function y equals to 1 by x. Again, in this function, if we substitute any value for x, you will get y. But if you substitute x equals to 0 into this function, y will not exist. Is that clear?
Yeah.
Yes.
X equals to 0 is not, the domain is not in the domain of this function, but rest of the numbers are in the domain of this function. You can write it in words like I just said. Otherwise we can write it mathematically. This is not the topic how to write it mathematically. The topic is just to know what is domain and range. So for example, I give you another problem. Let's say y equals to 1 over x square minus 1. We need to find out those values for x against which our y does not exist. We know that we cannot divide anything by 0. If we divide anything by 0, it goes to infinity. So we have to avoid this form, and y will not exist. Y will approach to infinity when this function, this denominator, this part will be 0. So we have to avoid, we have to ignore those values, and when this function will be 0, we can get x square equals to 1. From here we can get x equals to plus minus 1. So when x will be 1 or minus 1, y will not exist. Is that clear? So the domain of this function, we can say that the domain of this function is set of all real numbers except x equals to 1 and minus 1. Understand? Any questions so far?
It's clear.
Okay, good. So here you can see that I think I wrote so many things on this PPT. I tried to open a new PPT. Uh, you can see my computer, how many things I have saved for you guys. No? This is for, this was chapter. Yeah. Can you see now? Hello?
Hello.
Yeah, please keep talking, give me some responses so that everybody is listening. Otherwise, it feels like I am talking to myself. It is,
Okay.
this online teaching is quite strange. So I don't know what was going on in the group. I did not see any message, but I saw some of the messages and I came to know there was some confusion, or like that you need to ask a lot of questions, but you don't have a lot of time. You need have limited time, so don't worry about that. For example, this if this meeting ends at like after 120 minutes or after 1.5 hours, we can start immediately a new meeting, no problem. So you can ask as many questions as you can. Is that clear to everybody?
Yes.
Okay.
Yes, sir.
Okay. Example one: a function and the derivative and its sign chart. For example, you are given this function f of x equals to x cubed minus 3x. Now, if we take its derivative is 3x squared minus 3, and we can further write it into this form. Understand? Now, if we make the graph of this function, and you know how to make the graph, you can substitute different values for x. Let's say if you substitute x equals to -1, you can get y. You can substitute x equals to +1, you can get y, and then you can join those points. When you will make the graph of this function, it will be like this. Okay, the graph of the function and the sign chart for the derivative is shown when scanning from left to right. If we see from left to right on intervals where the graph rises, you can see that graph is rising from -2 to -1. You can see graph is going upward. Understand? And after -1, graph is decreasing from -1 to 1. From -1 to 1, you can see graph is still decreasing. Now from 1 to 2, graph is increasing. Understand? Is that clear?
Yes.
The point or the intervals where graph is increasing, your derivative will be positive. You can see here now from -2 to -1, the function f of x is increasing. So here we write derivative is positive. You can see we have positive signs. So from -infinity to -1, function is increasing, so derivative is positive. Now from -1 to 1, function is decreasing. From -1 to 1, function is decreasing, so derivative will be negative. Derivative will be negative. So from 1 to 2, function is again increasing, so derivative will be positive. So if I summarize this, if function is increasing, if function is going upward, then derivative will be positive. If function is negative, or if function is decreasing, then derivative will go down, right?
Yeah.
Okay. So you can see here now, for the interval AB, like in the previous slide, AB means this interval from -infinity to 1, AB. That is what he means by A and B. Is that clear? This is AB. This is AB. He is denoting it for the intervals. So for the intervals A, B, if f dash is greater than 0, if f dash is greater than 0, then f is increasing. And if f dash is less than 0, then f is decreasing. If you have any question to understand this statement, let me know. This is very important statement. You have to remember throughout this lecture. If f is increasing, for example, we have a function, graph of a function, f is increasing function, f is increasing, so derivative will be greater than 0 or derivative will be positive. If function is decreasing, then derivative will be negative. And we can read it the other way around as well. If derivative is greater than 0, if derivative is positive, function will increase. If derivative is negative, if derivative is less than 0, then function will decrease. You can see here When derivative is positive, function will increase, means the graph will rise. It will be of this form, something like that. If derivative is negative, the function will decrease and the graph will fall and it will take forms like this. Is that clear?
Yes.
Okay. Now, look at here. We have a function. We have a function f of x equals to 8x minus x squared. It says that which values of x corresponds to a horizontal tangent line. Horizontal tangent line where derivative is 0. So we take its derivative. If we take its derivative, derivative of 8x is 8, derivative of x square is 2x. We put derivative equals to 0. If we put derivative equals to 0 means 8 minus 2x equals to 0. It gives us x equals to 4. So the horizontal tangent is at x equals to 4. If you substitute x equals to 4 into this function, it will be 32 minus 16. So f equals to 4 is 16, which means that the horizontal line will be at 1, 2, 3, 4. And if 16s come here, so horizontal line will be here. Is that clear how to draw the horizontal line? If you have any question, please let me know.
Okay.
Okay. So now, what is this? Okay. Anyways. So we are given a function now for which values of x in part B, same question, part B, for which values of x is function increasing and decreasing. We know that when derivative is positive, function will increase, and we know that when derivative is negative, function will decrease. So we see that if the function is increasing when derivative is positive, when derivative will be positive, when 8 minus 2x will be greater than 0. So it gives us that 8 greater than 2x because this 2x will move there. So 8 is greater than 2x. From here we can conclude that x is less than 4. X is less than 4. Whenever x will be less than 4, function will increase and derivative will be positive. We can make interval that here if it is 4, less than 4, this is negative infinity, this is positive infinity, less than 4 is here, greater than 4 is here. So less than 4 function will increase and derivative is positive. When derivative is positive, we write positive signs. Now we see that what happens when derivative is negative. When derivative is less than 0, when derivative is less than any question in this slide, we can jump into the next slide then. Hello.
It's clear for me.
Okay. How many students in the room? It seems that I'm only teaching you.
9
There's 10
students
in the room.
so far.
Huh?
Oh yeah, nine students.
9.
Okay, so please, if you have any question, you can just ask me at the spot. Just hold on. क्या हुआ? ठीक है सर?
बस ठीक है किराया आगे पीछे और पैसे पूरे नहीं हो रहे थे ऊपर नीचे हो रहे थे बच्चे को क्या है कर रहे हैं ठीक है 100 या 200 का
ज्यादा दे दिए उसको?
नहीं मेरे पास ठीक है
बोलो ना जी.
ठीक है मेरे पास
Okay.
ठीक है
Okay, so we can jump into the next slide now. Look at here, we have drawn a tangent line. When x was 4, our function's value was 16, so we can draw a tangent line like this. We can draw a tangent line What happened? It is not responding. Just wait a moment. Okay. So okay. So here we can see that this is a tangent line. We put derivative equals to 0, we get x equals to 4. We substitute x back into the function, we get 16. So it tells us that 4 is here, 16 is here. So that is the tangent line, or so called the maximum point of the graph. Okay, now another very important definition in the exam, you will be asked to find the critical numbers, the critical values. So like domain and range, this is also very important from exam point of view. You should know how to calculate the critical numbers. A real number x in the domain of f. This is very important sentence. It should be in the domain of function. Any number should be in the domain of f and such that f dash equals to 0 or f dash does not exist is called the critical number. Is called the critical number. I will explain this definition through an example. It would be easy for you. For example, uh, let's say I write a function y equals to x squared minus 1. We take its derivative, a real number x in the domain of f such that f dash of x equals to 0. F dash of x, definition says that f dash of x equals to 0. So we take that, you can denote it by y or f, no problem. We can denote it by f. If we take its derivative, who can tell me the derivative of 1 over x squared minus 1 immediately? Hello? Hello? Can you hear me? Hello?
Yeah.
Yes, it's 2x minus 2, right?
The derivative is
To the power of
minus,
Minus
minus
1 over
2x.
x minus 1.
can you tell me the derivative minus 1 x squared minus 1 minus 2 2x.
Oh.
So the derivative is minus 2x over x squared minus 1 whole square. So this is the derivative of this function. Now it says that put derivative equals to 0. When you put derivative equals to 0, you will get minus 2x over x squared minus 1 whole square equals to 0. From here you can get x equals to 0. Understand? Now this is the critical point. This is the critical point. The critical point is which we get after substituting derivative equals to 0. But one condition is not satisfied here, that if we substitute x equals to 0 into the function, it will not be undefined. So I take one more example, which would be even more simple. Let's say y equals to 1 over x. If I take its derivative, it is minus 1 over x squared. And now we put our derivative equals to 0. So minus 1 over x squared equals to 0. So this function also does not exist. Let me see any other example to explain it even in a simple way. Or we can solve example which is given in the PPTs. If you have any question regarding this,
So I have a question. So the negative 2x divided by x squared minus 1 squared equals 0 thing, and
yeah,
you wrote x equals 0, right? Is it because negative 2x becomes 0? Like we should calculate based on the
that,
not denominator, right? We
no,
have
no,
to.
we will take cross multiplication and denominator will vanish because the other side have 0.
Wait, so you say it's because negative 2x equals 0. That's why x equals 0, right?
Yes, 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 yes.
Okay, not x squared negative 1. Okay, I got it.
Okay, so here we can see that a simple example like f of x equals to 1 plus x cubed. Find the critical numbers. I repeat my words. To find the critical numbers is very simple and very easy and very important from exam point of view. If you are asked to find the critical numbers, you can take the derivative of function. Like here, we take the derivative of this function and we put that derivative equals to 0. Like we take derivative and we put it equals to 0. You can see that f dash is equals to 3x squared. We put it equals to 0 and we get x equals to 0. Now, the definition of partition numbers. Partition numbers are those numbers which would be critical numbers if those numbers are in the domain of f. What I said, if you don't understand it, please ask me questions. This is very important statement. So how we can make the partition numbers? Like x equals to 0, we will see before 0 and after 0. Here we write 0. Before 0, we will see that the derivative is positive or negative. You can choose any number before 0. Let's say I choose -1. Before 0, we can make a chart x and we see what is the behavior of derivative. Before 0, give me any number before 0.
Negative
3.
Negative.
1.
Okay. Okay, so we see the derivative, the behavior of derivative at -1. So 3 times -1 squared. So it is positive. Derivative at -1 is positive, right?
Yeah, it's positive.
At
Yeah.
-1, derivative is positive. You can see that you can choose any number before 0, your derivative will be positive. So that is why we have here positive numbers. That is why we have here positive numbers. So it means that when derivative is positive, what we have discussed before, your function will be increasing. Your function will be increasing. You can jump in back into this definition. I am talking about this definition. You can see that when your derivative is positive, your function will be increasing. Understand?
Yes.
So now we check after 0. You can choose any number after 1. Let's say we choose any number after 1. I choose for simplicity again 1. So again f dash of positive 1 is also 3, which is also positive. So it means that after 1, after 0, derivative is again positive. So our function is again increasing. Is that clear? Is that clear?
Yeah.
Yes.
Okay. So
Yes.
0 is the partition number which make partitions like before 0 and after 0. And every partition number is not a critical number, but every critical number is a partition number. It is just like that, that every student of Tsinghua University, is not a CIP student. Understand? But
Yes.
every CIP student is a student of Tsinghua University. Is that clear?
Yeah.
Yes.
So similarly, every partition number is not a critical number, but every critical number is a partition number. Now you should ask me here, how do we know that which partition number is a critical number? We will see that is that critical number is in the domain of function. Now we have already discussed in the beginning of this lecture, how do we know the domain? The domain of this function is set of all real numbers. So this x equals to 0, this 0 belongs into the domain of this function. So we can say that yes, this 0 is a critical number. This is how we find a critical number. Is that clear? Any question? I need some questions from you.
So far it's clear.
Okay.
It's difficult later in the PPT, I think.
No, just ask me questions. Later, difficult or easy, we can solve different examples. You can go through from it. Then I think things would be easier. And the more you will solve, the more you will be familiar with this. It is not difficult. Believe me, it is very simple because I am explaining each and everything. I am explaining all the concepts from exam point of view. To solve the questions, it is very simple. You can see, you just take the derivative, put it equals to 0, solve it for x. We are just discussing its analysis. That is why you are,
Yes.
maybe you feel it is a difficult, but as long as question solving is concerned, it is very simple, believe me.
Okay.
uh, we
All right.
Yes, we take another example. Find, it says that find the critical numbers of f. We find the critical numbers of f, the intervals on which f is increasing and those on which f is decreasing. F will increase when derivative will be positive. As we know, f will decrease when derivative would be negative. We take its derivative. We take the derivative of this function. The derivative of this function is this. Now, the derivative f dash is continuous for all x except x equals to 1, which gives a 0 denominator. How do we know that if we substitute x equals to 1 into this function? Can you see, if I substitute x equals to 1 into this function, your derivative does not exist. Is that clear? Is that clear? It follows that
Yeah.
x equals to 1 is the only
Yes.
partition number. It follows that x equals to 1 is the only partition number for f dash. Since x equals to 1 is in the domain of f, yes, so x is the only partition number, is the only critical number here. It should be critical. It is wrong. It should be critical number. I was doing something different here on these examples. What we were doing, you see that here, first we discuss this example, or I discuss this example there on the same page, then it would be easy for you. For example, here you can see that if I write another example, let's say y equals to 1 over x square minus 1, we were taking its derivative was minus 2x over x square minus 1 whole square. Now this derivative f dash does not exist at x equals to 1 and minus 1. Understand? F dash does not exist at x equals to 1 and minus 1. So these are the partition numbers. What we will do, we will write here minus 1, we will write here 1, and we will choose any number before minus 1. You can choose any number before minus 1. You can make here chart. You can see that your derivative is positive or negative. You can choose any number before minus 1. Let's say we choose minus 2. We substitute minus 2 into this function and we see is it positive or negative. It is positive. So derivative is increasing here. Derivative is positive, so function will increase. Now we choose any point between minus 1 and 1. We choose 0. If we substitute here 0. 0 is neither positive or negative. So for simplicity, I choose 0.5. I choose 0.5, and then I can see that is it positive or negative. It is negative. So here your derivative is negative, so function is decreasing. And then I choose again 2. So if I choose again 2, your function is negative. So still function is decreasing after 2. So this is called partition numbers and intervals. This is how we make intervals. So what are the intervals? Minus infinity to -1, then -1 to 1, and then from 1 to infinity. These are the intervals. This is how we make interval. -1 to minus infinity to -1. This is first interval. -1 to 1. This is the second interval, and 1 to infinity. This is the third interval. So function is increasing or derivative is positive on this interval. Function is decreasing or derivative is negative on this interval, and function is again decreasing on this interval. Is that clear?
Yes.
Okay, so the derivative f, okay, now we can jump into some other examples. Find the critical numbers of f, the interval on which f is increasing and those on which f is decreasing. We have just solved this example. I have solved this example for x minus 1. This is x minus 2. Nothing changed. We can take its derivative. When we take its derivative here, it should be the sign of derivative. They removed it. This is f dash of x. If we take its derivative, sorry, this is not, this is f dash of x. F dash of x is this. Our derivative is not defined at x equals to 2. If we substitute x equals to 2, f dash of x will not exist. So to find the partition number for f dash, note that f dash is non-zero for all x, and it is undefined at x equals to 2. You can make similarly a line. You can say 2. You can choose any number before 2. You can choose any number after 2. Substitute it into the derivative and see either its signs are positive or negative. This is how we find the in partition numbers or intervals or critical numbers. So here now, after finding critical numbers, we see that where is local extrema and where is local minima. This is very much associated with the same thing. You can see that here, if you look at this graph is decreasing, further decreasing, then increasing, then decreasing, increasing, decreasing, and decreasing. If you look at this function from minus infinity to C1, function is decreasing. Understand? Right?
Yeah.
From C1 to C2, again function is decreasing. From C2 to C3, function is increasing. C3 to C4 decreasing, C4 to C5 increasing, C5 to C6 increasing, C6 to C7 again decreasing. The lowest point is C2 and C4. The highest point is C6 and C3,
C6.
right? So these are local extremas. Extreme means it would be lowest or it could be highest. Local extrema. I don't want to read these definitions because you would be unable to understand. We can explain these things through a simple example, then it would be easy for you. Local extrema and critical numbers. This is so-called a theorem. If f of c is a local extrema, if f of c is a local extrema of the function, then c is a critical number of f. What does it mean? I will explain it through a simple example. Okay. First derivative test. Okay. I summarize whatever we discussed so far. I need your attention. If you were confused so far, no problem. But I need your attention. I need everybody's attention now, because we were doing all these definitions to apply this first derivative test. Everybody is attentive now?
Yes.
Yes.
Okay.
Yes.
So before you were sleeping, you were worried,
No.
but now I need your attention. Everybody get up and look at here. Critical points. How do we find critical points? If you are given a function, you take the derivative of that function, you put derivative equals to 0, solve it for x, you will get some values for x, x0, x1, I'm just writing it randomly, right? Then you will see if x0 and x1 is in the domain of f or given function, I'm talking about this function, then it is a critical number. And these are also called partition number. As I gave you an example that every student of Tonghua University is not a CIP student, but CIP student is the student of Tonghua University. Okay, this is how we find critical numbers. After finding critical numbers, we write them on a straight line. We write here x0, first critical number, we write here second critical number. Now we choose any number before our first critical number and we substitute it into our derivative. And we see our derivative is negative or positive. If it is negative, then we write negative like this here you can see. If it is positive, then we write positive. Now then we choose any number after x0 and we see the behavior of our derivative. If it is negative or positive, we write it accordingly. Understand? Any question up till here?
No.
Okay. Now, if our derivative is first negative, then positive, we say that it is local minima at this point. It is local minima at this point. This is called first derivative test to locate local extrema, local minima or maxima. We will say that it is local minima at this point. Is that clear? If our derivative is first negative, then positive, we say that it is local minima. And if our derivative is first positive before the critical number and then negative after the critical number, then we say that it is local maxima. Then we say that it is local maxima at C, right? Right?
Yeah.
Okay.
Yes.
So, if it does not change its sign before and after, we say that it is neither maxima nor minima. Likewise, if it does not change its signs before and after, it is negative, so we say that it is neither maxima nor minima. Okay. Horizontal tangent. For a function, we have already discussed how to draw a horizontal tangent for a function f of x when the derivative of f dash c equals to 0 for some value of at x equals to c. There is a horizontal tangent at x equals to See, for example, I gave you an example like, uh, let's say that you have a function y equals, or function x, f of x equals to x square minus 1. We take its derivative is 2x. We put derivative equals to 0, 2x equals to 0, so x equals to 0. We substitute x equals to 0 into the function, so it is minus 1. So the tangent line at x equals to 0 would be at minus 1. For example, this is the graph, minus 1 comes here. So this would be your tangent line. At x equals to 0, this would be your tangent line. This is how we draw the tangent line of a function. Okay. So here we solve one example. Find the critical numbers of f. Who can tell me? I think it is already written, you can see. Part A. Part A says find the critical numbers of f. You are given a function. To find the critical numbers, we take its derivative. Very easy. 3x squared minus 12x plus 9 equals to 0. We take out 3. We get x squared minus 4x plus 3. We factorize it. We get x equals to 1 and x equals to 3. Now, x equals to 1 and x equals to 3 is in the domain of this function. So x equals to 1 and x equals to 3 are critical numbers. Is that clear?
Yes.
Abu, how?
Yes.
Yeah.
How?
How? It's been long I didn't speak any Chinese. I'm craving for it. Okay. So now we want to locate local maxima and minima. What we do, we draw a line. We write our critical numbers 1 and 3. We write before 1, and here you can make table f dash of x. Before 1, you can choose, let's say 0. Understand?
Yeah.
Yes.
And we see the behavior of our derivative. 3 times 0 squared minus 12 times 0 plus 9. So it is 9. 9 is positive or negative?
Positive.
So at 0, it is, our derivative is positive, right?
Increasing. Yeah.
So before 1, it is positive. Is that clear? Now
Yeah.
after 1 we can choose, let's say 2. So we see the behavior of our derivative. 2 times 4, 12 minus 24 plus 9. It is minus 3. So minus 3 is positive or negative?
Negative.
Negative. So after 1 it is negative. At 2 it is negative. Now this, we have discussed the first critical point. We chose before and after 1. Now we discuss the second critical point, 3. Before 3 we can still say 2, and we have already checked it is negative at 2. Now after 3, After 3, we can choose, let's say, number 4. And we see the behavior of our derivative at 4. So 3 times 4 raised to power 2 minus 12 times 4 plus 9. What is it? 48 minus 48 plus 9. So it is plus 9, which is positive. So it is positive after 3. Understand?
Yeah.
Is that clear? Now we will decide. Now we will decide that at 1 is it local minima or maxima, and at 3 is it local minima or maxima. Now if you look at 1, can you see this bar chart?
Yeah.
Yeah.
Yes.
Before 1, first it is positive, then negative. So it is local maxima at 1. We will say that local maxima at x equals to 1. Now, if you look at 3, now who can tell me at 3 how the function is behaving?
Do you mean after 3?
Now, at 3, you can see before 3 derivative is negative and then it is
It's
Positive.
makes sense.
positive. So it is local minima. Local minima. Understand? Look at,
Yeah.
you can look at this definition. Now I think it would be easy for you to understand after solving this example. At 1, you can see our first critical point was 1. Understand? Right? Before 1 derivative was, our derivative was positive. After 1, our derivative was, can you hear me please?
Negative. Negative.
Negative. So in that case, we say that local maxima at 1. Understand? This is how our
Yeah.
function is behaving. This is how our function is behaving at 1. First, before 1, it was positive. After 1, it was negative. So if derivative is positive before, negative after, then we say that local maxima at that point. This point is 1. And the second condition was, this was the second condition. First, at 3, this was the second condition. At 3, first it was negative, then it was positive. If it is like this, first negative, then positive, then we say that local minima at that point. I hope it is clear now.
Yeah.
Is that clear?
Yes.
I have a question about the brackets.
Which bracket?
There's 2 types of brackets.
I cannot see any bracket on this slide.
Okay, not this one. Yeah.
No, if you have any question about this slide, you can ask me.
Oh, so just to make sure, I want to ask something. So here on this slide, x equal 1 and x equal 3, and if you want to check if it's in the domain, you can simply put those numbers to the fx, right? And if it's not 0, it means it's in the domain, right?
Listen it very carefully. Everybody should be attentive. This is very good question. Are you Carolina?
No, I'm Chandra.
Oh, Chandra.
No, yes.
I give you 1 point for this. I give you 1 point for this. Do
Yes,
remind me in the final. I will give you 1 point. This is very good question. I must say I appreciate it. Now everybody must be attentive, and I want you to repeat it again. Chandra,
Yeah.
repeat this
Oh,
question.
should I ask again?
Yeah.
Okay.
I want everybody to listen
So,
to me.
to make sure if it's a critical number, So here you can see x equal 1 and x equal 3. And you said it should be in the domain. So we
Yes.
can put those x numbers to the fx function. And if it's not 0, it means it's in the domain. Is it or not?
Just a small mistake. What is that
Yeah.
mistake? You substitute x equals to 1 and x equals to 3 into this
Mhm.
function.
Yeah.
Into this function. If it does not exist, then x equals to 1 and x equals to 3 are not in the domain of this function. If it is 0, still fine. 0 is a number. 0 is a solution. Understand?
Oh, okay.
Understand?
Mhm.
If it does not exist, for
Yeah.
example, if you substitute x equals to 1 into this function and you see that it is undefined, if it is infinity, then you will say it is not a critical number because it is not in the domain of function. Is that clear?
Yeah. But how do we know if it's infinity? Like,
Yeah. You can substitute any number into this function. It will never be infinity because it is a
oh,
right. If it will be
mm,
infinity whenever you will have a ratio or whenever you will have a function like square root. I give you a quick example. Uh, let's say you have a function y equals to, or f of x equals to x minus 1. You substitute x equals to 1 into this function, it will be 1 over 0, which is undefined,
mm,
So x equals to 1 is not a critical number. It is a partition number, but it is not a critical number because it is not in the domain of this function. Now you substitute x equals to 3. If you substitute x equals to 3, 3 minus 1, 1 by 2, you get an answer. So it means that x equals to 3 is a critical number,
yeah.
right? Whatever you
Yeah.
said was 100% correct, except this. You said that if f is 0, then x equals to 1 and x equals to 3 are critical number. No, it will be a critical number when it will not be a critical number when it does not exist. Is that clear?
Yes.
Very good
Thank
question,
you.
Sandra. I really appreciate it, and I want others to ask these type of questions, and they can win 1 point or 2 points. Right?
Yeah.
Now we see this example. We have already did this. You can see that before 1 derivative was positive, after 1 it was decreasing, and then after 3 again it was increasing. So the local maxima at x equals to 1 and local minima at x equals to 3. Understand?
Yes.
So find the critical numbers of f. We have already obtained the critical numbers for this x equals to 1 and x equals to 3. It says find the local maxima and minima. We have already obtained local maxima and minima. Now it says sketch the graph of f. When we sketch the graph of f, how do we sketch its graph? Local maxima at x equals to 1, it is local maxima. When you substitute x equals to 1 into this function, you will get 5. So at x equals to 1, you have maximum tangent. This is the tangent line. This is how we draw a tangent line. And at x equals to 3, it was minimum. So when you substitute x equals to 3 into this function, you will get 1. So this is your lowest tangent. Understand?
Yes.
Yeah.
Okay. So here we can see some examples related to economics. We know that when derivative is positive, function is increasing. Understand? right?
Yes.
So look at here. This is derivative. This is derivative. From this point to 10, derivative is negative or positive? Who can answer me? Who can win 1 point, one more point?
Negative.
Negative.
Uh, who said negative?
It's increasing.
Yeah,
And
you take it. You take it. You were first.
no, I can. I don't mind. I can give. I have a lot of points. You can give as well. You can get as well. I think
No,
it's
but she answered. But she answered before me, so she should take it.
okay. Okay. If you don't want to take it, it's okay. No problem. So okay. So by the way, it was Jonathan, right? Okay. Anyways.
So what?
Yes, I just answered, but she answered before me, so
So Chandra, one more point for you. You can see
Thank
here.
you.
You can see here E dash is negative from, because it is below this line, it is below this x-axis. If E dash is negative, when our derivative is negative, function is decreasing. Function is decreasing. So if you make the graph, you can say that function is decreasing. Aa jao beta. You can say that function is decreasing. Now from 10 to 50, from 10 to 50, your derivative is positive because it is above the line. When derivative is positive, our function is increasing. Our function is increasing. And then from 52 onwards, derivative is again negative. So it means that your graph will again decrease. This is how we make the graph. Is that clear?
Yes.
Yeah.
Yes.
So you can see, you can draw an approximate graph according to the derivative. First function will be decreasing because derivative was negative, then derivative was positive, so function was increasing, then again derivative was negative, so function will decrease. So now we solve some examples or questions from the assignment, from the exercise, and thing would be more clear. So like here, can you see the book?
Yeah.
yes, yes.
For example, if I come to question number 9, identify the intervals on which f of x is increasing. You can see that this function is increasing from a to b. It is going up. So from a to b, function is increasing. Then from b to c, it is decreasing. Then c to d, again it is decreasing. From d to e, it is increasing. From e to f, it is increasing. From f to g, it is decreasing. From G to H, it is again increasing. Understand?
Yep.
Yeah.
Now it says that identify the intervals on which f of x is decreasing. So you can identify increasing and decreasing. It is very simple. I have just mentioned it. Now identify the intervals on which your f of dash is less than 0. When f of dash is less than 0, now you can see that for question number 11, when our derivative is negative, when function is decreasing. Understand? Is that
Yeah.
clear? This is very simple. definition we started, I just go back to this definition. When derivative is negative, your function will decrease. I am talking about this. When derivative is negative, function will decrease, right? Now look at this. Where function is decreasing from B to D. Understand?
Yeah.
Yes.
Function is decreasing.
Sir, I have a question.
Yes.
What about when the derivative is equal to 0? How then does the function operate?
It gives us the critical point at that stage. We find critical point when derivative is 0.
Okay.
Good point. Good question. But not for the 1 point. Okay.
It's
So
fine.
okay. So similarly, question number 12, identify the intervals where on which f dash of x is greater than 0, where function is increasing, f dash of x, f derivative is positive. So function is increasing from a to b, then from e to f, and then from g to h. Is that clear? Right?
Yes. Yes.
Yeah.
Now identify the x coordinate of the points where derivative is 0. Where derivative is 0, those points where this function is crossing x-axis, these points are the points where derivative is 0. And identify the x coordinate of the point where derivative does not exist. I don't think so. Yeah, you can see these sharp edges here. Derivative does not exist on these sharp edges. There is another theory behind this. I don't want to get into this, but just to let you understand how we can identify derivative and function through the graphs. Okay, so we can directly jump into these problems. For example, question number 47 to 58. It says that find the intervals on which f of x is increasing, the intervals on which f of x is decreasing, and the local extrema. For example, if I how can I delete it? Let's say we solve this first example, this first problem where it says that f of x equals to x4 minus 4x cubed plus 9x. You find the intervals on which f of x is increasing. To do so, we take its derivative. Its derivative is 4x cubed minus 12x squared plus 9. So we put this derivative equals to 0, which means that 4x cubed minus 12x squared plus 9 equals to 0. Or I think
2x minus 3
no.
square.
And because oh, to solve this we need synthetic division, and we don't want to get into this. We can skip these problems and we can jump into the other ones where we don't need to use synthetic deviant. Let's say, I think in all these, he's saying use the graphical calculators. This guy add the horizontal tangent line. Find the intervals on which the function is increasing, on which function is decreasing, then sketch the graph, add horizontal tangent lines. Okay. So for example, if we solve number 50, let's say we solve number 56. Do you know why I didn't solve this problem? Who can tell me? Who can tell me why I did not solve question number 47? Nobody is answering. Just say we don't know, or if you know, you can just tell me.
I don't know.
Undefined, perhaps.
Because in your course, either fundamental mathematics, either basic mathematics, or even in statistics, we are not studying this equation. X cubed plus 2x plus 1. We are not studying any cubic equation. We have different rules to solve it for x. We are covering, in our course, we are restricted to only this equation. The maximum power should be 2. So in problem 47 to 52, particularly in 47, the power was 3. So because we are not covering this, it means synthetic deviant. If somebody is interested, you can just Google it. Synthetic deviant is very simple. But because it is not in your course, so that is why I just removed that problem. So we just limit ourselves to the quadratic equation. Like here you can see in 56, if I take its derivative, 3x squared minus 12. Now this is a quadratic equation. We put it equals to 0. So 3x squared minus 12 equals to 0. X squared equals to 4. So x equals to plus minus 2. Now since at x equals to 2 and minus 2, our function is defined. Defined means it exists. Either you substitute x equals to 2 into this function, you will get a number. Either you substitute x equals to 2 into this function, you will get a number. So we can say that either you, since x equals to 2 and x equals to minus 2, is our function is defined. So x equals to 2 and minus 2 are critical numbers. So we can say that they are critical numbers. Then it says that find the intervals on which f of x is increasing and the interval on which f of x is decreasing. So here we can see that now we have two critical numbers, 2 and minus 2. We will see before 2, from we will say that from minus how we can do that, from minus infinity to minus 2, we can choose any number before minus 2. Understand?
Yeah.
Yes.
I think let me share your whiteboard, because here it is difficult for me to write. you see now whiteboard?
Yeah.
Yes.
Yes.
Okay, so the problem was that f of x equals to x cube minus 12x, x cube minus 12x plus 2. So first it was saying that find the interval on which function is increasing or decreasing, or we can find local extrema or minima. We take its derivative 3x square minus 12, put f dash equals to 0. So it is 3x square minus 12 equals to 0. So x square equals to 4, x equals to plus minus 2. We draw interval minus 2 and 2. Now we see that before minus 2, we can make here a table. Before minus 2, let's say we choose any number minus 3. So f dash at minus 3 is 9, 27 minus 12. It is 15. 15 is positive or negative?
Positive.
Positive.
So f
Yeah,
dash
positive.
Positive.
from minus 2 on the right side of minus 2, we can choose minus 1. So 3 minus 1 square minus 12. 3 minus 12, it is minus 9. So it is
Negative.
Negative.
negative. Now after before 2 we can say that we have already minus 1. Now we check after 2. After 2 we can say 3. So again it is positive. At 3 it is positive. So before minus 2 it was
Negative.
positive. After minus 2 it was negative. Before 2 it was negative. After 2 it was positive.
Positive.
So when derivative is positive, function is increasing. When derivative is negative, function is decreasing. When derivative is positive, function increasing.
Increase.
That is what he was saying.
Yeah.
Find the intervals on which function is increasing, and on the interval find the interval on which function is decreasing. Understand?
Yep.
Then it says sketch the graph and add the horizontal tangent lines. Now we want to sketch the graph and sketch the horizontal tangent lines. What are our intervals? From minus infinity to minus 2, function is increasing. From minus 2 to 2, function is decreasing, and from 2 to infinity, function was
Increasing.
increasing. Now here because in the question he is not asking about local extrema, but you can identify local extrema. When function is increasing then decreasing, it is local maxima. It is local maxima at x equals to minus 2. And if you look at for 2, before 2 it is decreasing, negative, then it is increasing. Local minima at x equals to 2. Understand? Then he says,
Yes.
sketch the graph. Before sketching the graph, we find the horizontal tangent at x equals to -2. Our function is, what is function? X cube minus 12x, x cube minus 12x plus 2. It is 8 plus 24 plus 2, and it is 18.
18.
And at x equals to 2, 8 minus 24 plus 2, it is minus 14. Now if we make the graph of this function, the graph will be, you can see that from minus infinity to -2 function is increasing. One, 2, 3, 4, -1, -2, -3. From minus infinity to -2, function is increasing. So it means that it is something like this. Function is increasing, then from -2 to 2, function is decreasing. From -2, no, it would be like this. So function is increasing, and then from -2 to 2, it is decreasing, and then again it is increasing. From here it will increase. This is how we can make the graph, or we can discuss it later, how to make the graph, and also the problems related to economics. I think restrict up till here, how to find the critical numbers, how to sketch it, how to find the local extrema and minima. If you have any question, please ask me. Hello?
The graph doesn't have to be accurate, right?
Yes, it
Just
is.
the values.
Yeah, it is an approximate graph.
Got it.
It is an approximate graph, and if I share my screen now, you can see that here. Problem 69 to 74. If you look at problem 69 to 74, it says that function 1 to 6 and their derivatives g1 and g6 use the graph shown in figure A and B, that each function fi with its derivatives. If you look at this function, look at here, f1. This is a function. This function is in,
Hello?
yes, hello?
Breaking up.
Hello? Hello? Hello.
Yes, we can hear you now.
No, you were gone for a while.
Sorry.
You disappeared, or it was lagging.
Okay, maybe. Um,
We couldn't hear you, or I couldn't.
now is it okay? Now is it okay? Is it okay?
Yes.
Okay.
Now it's okay.
Okay. If you look at this problem number 69 to 74, if you look at this one, this first one, function is increasing from left to right. It is increasing up till 0.5. Understand? So your derivative will be positive till -1. Your derivative will be positive till -1, and then function is start decreasing after -1. So your derivative will be negative after -1. We can see here, look at this graph, G4. If you look at F1 and if you look at G4, they are, the derivative of F1 is G4. Do you understand what I am talking?
Yes.
Yeah.
So
Yeah.
when function will increase, derivative will be positive. So function is increasing till 5, and or you can say till -1, function is increasing. So derivative will be positive till -1. Here you can see that derivative is positive till -1, and after -1 the function is decreasing. So the derivative will be negative after -1. Is that clear?
Yeah.
If you have any question, please you can ask me. Similarly, if you look at this example, which is application related, you have, for example, I think we had 1 hour and 30 minutes. Maybe they will end the meeting automatically. But if you want, I can arrange immediately a new meeting.
Okay.
Huh?
Okay.
Okay. So look at this. Can you see question number?
Is the graph ever like a flat line?
Yeah, it can be. It's a
In
constant.
what case?
It's a
Oh,
constant.
if it's a constant.
Yeah.
Okay, thank you.
So look at this 91. 100, 200, 300, up till 300. Can you hear me?
Yeah.
Yes.
When it would be end, just send me a message in the group. I will arrange a new meeting immediately. Okay.
Okay.
So from so 1, 2, 3, up till 300, function is increasing. Till 300, function is increasing, so our derivative will be positive. If we make its derivative up till 300, 1, 2, 3, up till 300, our derivative will be positive. After 300, it start decreasing, so derivative will be negative. So it's the graph of its derivative p dash of x will be like this. This is p dash of x. Is that clear?
Yes.
Now, if you look at 92, if you look at this 92, this is again a function. Function is increasing till 500. Function is increasing till 500. So 100, 200, 300, 400, and 500. So derivative will be positive till 500. After 500, it is decreasing. So it will be in the negative side. Is that clear? Any question?
So it's only when it's like the dash function, right?
Yes.
Okay.
Now we
Okay.
have a reverse function. For example, reverse means question number 93. Question number 93 says that you are given a derivative, right? You are given a derivative. If you look at this, derivative is negative up till 5, 10, 15. Till 15, till x equals to 15, derivative is negative. 5, 10, 15, which means that graph will decrease till 15. Then derivative is positive from 15 to 55. Understand? It means that then graph
Yes.
start increasing till 50. Then after 50, again derivative is negative, so it means that graph will start decreasing after 50. So the graph of this function is this one. So if you look at this, the basic thing, the very basic thing, uh, if I make the summary of everything, it is just like that. Function is increasing if f dash is, if its derivative is positive, function is decreasing if its derivative is negative. Our whole lecture was moving around these two lines. You can read it the other way around. If f dash is positive, if f dash is positive, if f dash is positive, function is increasing, then function is increasing. If f dash is negative, function is decreasing. Or the other way around, which we are doing right now, if f dash is increasing, then function is positive. If f dash is decreasing, function is negative. Is that clear? Is
Yeah.
Yes.
Yeah.
so you can solve some examples. You can solve examples from 33 to 42. Can you see the book?
Yes.
You can solve from 33 to 42 and also from 53 to 60. Okay. And then we can, I will I will try to solve some problems and I will share it in the group. And in the next tutorial on Wednesday, we will discuss the second derivative test, which is also very simple. And also in the next lecture, which is on Wednesday, we will discuss the real life application or problems related to the business side. So far you can solve, you can take this as an assignment, like question number 33 to 42, 53 to 60. I just dropped it in the group as well. Is that clear?
Yes.
Okay.
Yeah.
Any question?
No.
Not yet.
Okay, so let me take your attendance as well. Who is present physically? Uh, 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 uh. Okay, Stein, are you there?
Yeah. Hello.
Okay, Carolina.
Yes.
Okay, Chandra, always there. Lisa.
Here.
Okay, you didn't ask me any question. Crystal.
Yes.
Okay. Corwin.
Here.
Okay, Jackie. Jackie.
Yes, sir.
Okay, you always just get into the room and then you do something else.
No, it's my audio.
Tiffany.
Hi.
Okay, okay, it means everybody is there. So we can stop the recording.